Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Priya Khandelwal talking to us about interpretable and explainable AI. So without further ado, take it away, Priya.
Thanks, Pranav. So, hi everyone, I'm Priya, and today I'm going to be talking about a field of AI that has recently been growing a lot in importance, XAI, which is also known as interpretable and explainable AI. So throughout this talk, we're going to achieve three learning objectives. First of all, we're going to understand what XAI is and why we need it. We're going to also learn about some leading XAI techniques in the field. And also, you'll be able to understand how to find an XAI approach that fits your specific project needs. So the idea behind XAI is this pretty simple question. How do we know models are making decisions for the right reasons? And you might wonder, why as researchers or even as end users do we care about this? Like if a model is making a correct prediction, isn't that good enough? So let me give you an example of an issue that happened in 2014 that kind of demonstrates the need for XAI. So around that time, automated grading systems for exam essays were becoming really popular. And a lot of these automated systems were doing the gradings instead of human graders or human teachers. And overall, they were like doing a pretty good job. They were giving good essays, good scores, and bad essays, bad scores. But there was also writing like this that got a good score. So this paragraph shown here is a nonsensical sequence of advanced sounding words that was generated by a system called Babel. It was developed by some MIT students. And this paragraph follows the structure of a lot of good quality essays that automated grading systems are trained on, but it doesn't even make sense. Yet these grading systems gave this essay a really good score. And what this revealed was that the models that were trained to grade essays weren't actually learning about creative thought or advanced skill. They just picked up on some word patterns and sentence structures, and they gave that a good grade. And these were systems that were actively deployed in GRE exams and TOEFL exams and SAT exams. So it definitely became a huge issue. And this problem isn't limited to automated grading systems. For really high risk fields like medicine, this is especially relevant. Not only do accurate predictions save lives, but knowing why a prediction was made a certain way, having that transparency is really important to introduce trust and accountability in these decision-making systems. So there's, a lot of different ways to approach XAI as a topic, but I'm just going to dive into a couple popular or foundational techniques today that are used to validate model interpretability and understand what models are doing. Before I get into more details over what XAI is, just a broad overview of what we're going to talk about today. I'm first going to give you a high-level description of XAI. Then we're going to explore 5 well-known techniques: saliency, LIME, SHAP, counterfactuals, adversarial, and prototype, and also understand what we can do moving forward. So broadly speaking, interpretability itself is the ability to determine cause and effect for an ML model. And explainability is kind of a subset of that. We're trying to determine whether a node or input or layer represents something in a model and what it represents and how important it is. And you don't always need to know explainability, but it can definitely be really helpful. So for example, explainability might help you understand in a stroke prediction model that age is like 80% important and BMI is maybe 10% important. Or it could be really useful in specific model use cases. So for example, if you're trying to train an AI model for fairness reasons, you might want to understand the explainability of your model to make sure that the decisions that it's making is not taking into account like race or gender or anything else that you want to keep out of the decision-making process. For most of the presentation today, I'm going to focus on interpretability as a whole, but you're going to see explainability come up through some of the techniques that I'm going to be talking about. So when it comes to interpreting a model's decisions, there are kind of 2 camps of approaches. The first is the intrinsic camp. So this means that the models that we're trying to understand are inherently human interpretable. So examples of this could be like a linear regression model where the weights of the coefficients kind of tell you how important each feature is to the final prediction, or different information theory metrics like entropy. So if you have a split in a decision tree, you know how meaningful it is to the final prediction. And overall, these models are really easy to understand, but the downside of that is that they have constraints on their complexity, and it's kind of hard to actually achieve good results on difficult classification tasks. So that brings us to our second kind of approach, which is post hoc. So it's, as the name suggests, something that you do after you've already trained your model. This approach works really well for any complex model that you're working with that is making some sort of prediction or classification. You can apply a second model on top of that to analyze the results that are coming out of this model after it's been trained. Generally, complex models can be grouped to two general categories: black box or white box. If you're making a post hoc explainability approach for a black box model, that means you're mostly going to be working with the inputs and the outputs coming out of the model. The internal aspects of the model are a black box to you. But if you have a white box model, that means maybe you have access to some internal information like weights or gradients. And that could also help you further understand how the model is making decisions, after training. So the other interesting thing about black box and white box models is because black box models are so ambiguous, they can be used kind of with any architecture, but a lot of post hoc white box approaches are limited to a certain architecture. For example, if you're using a post hoc model or a post hoc XAI technique on a model that needs feature map information, it probably won't really work well on a random forest classifier. So today we're going to be focusing primarily on post hoc approaches because that's relevant to the increasingly complex models that are being developed within the AI space. And even looking within post hoc interpretability methods, there's a lot of ways to classify, or categorize the XAI approaches that exist. Some are based on use case or some are based on utility. And I think after looking at a few different sources, there are maybe 4 general categories where you can group together XAI techniques. So we have scope, purpose, data modality, and agnosticity. So scope refers to whether our post hoc technique can explain our model's overall, or if it can explain why one single prediction was predicted the way it was. Purpose and agnosticity are related to what I talked about earlier, with white box models being very specific and black box models being very broad and applicable. And then data modality, as the name suggests, allows for XAI techniques that are particularly useful for a certain type of input data. So you can have tabular data, time series data, image data, or text data. So I actually won't be presenting XAI techniques using these 4 categories. Rather, I'm actually going to break down our discussion into models that interpret features and models that interpret training inputs. And as we're talking about these 2 different kinds of XAI techniques, I'm going to dive deeper into the scope, purpose, data modality, and the agnosticity of each approach. So we are first going to start off with saliency. So this is an attribution approach for features that has generally a local scope specific to whatever class you're looking for. It's white box. In particular, it works really well with image and text inputs. So you can have CNNs or vision image transformers. And it can, depending on the type of model you're working with, it can be really specific to a certain type of CNN, or it can be really broad. Saliency maps, as you can see from the image over here, give us a sense of how important each feature or each pixel is for a certain prediction. Saliency maps started off at their bare bones with vanilla gradients. So this approach here is actually very similar to backpropagation. So you can take a look at this equation here. What it's basically saying is that we can take the gradient of each outputted prediction pixel with respect to the input. Or I'm sorry, with the prediction class with respect to each input pixel. And that gives you a sense of how much each pixel contributed to the prediction at the end. And it gives you a way to quantify how important each pixel was to the final prediction. And this is a highly nonlinear process because during the prediction pipeline, we have a lot of like activation layers like ReLU. And that way, if a pixel is not particularly important to the prediction, we know that its gradient will come out close to 0. And if it is important, it'll be a really high value. And visually, that ends up being represented as like red areas for high importance and blue areas if the gradient comes out to 0. And this approach has been really, really helpful, but it's not very class discriminative and not very high resolution. So there's a lot of ways to work from here. As you can see, there have been a lot of different developments made on top of the vanilla gradients approach, but today we're specifically going to focus on CAMs and GradCam. So the idea of CAMs are basically that when you put an image through a convolutional neural network, each convolution is generating a feature map. And instead of putting those feature maps through a fully connected neural network at the end, you can put a global activation pooling layer. And in doing so, you get weights for each feature map. And those weights can help you determine how important each feature map is to the final prediction. And you generate this class activation map. And this is far more granular than the vanilla gradients approach. And GradCam extends on this CAM approach by using gradients as weights instead of that last GAP layer. So overall, this approach has been really good, and it's not dependent on any one architecture. So it increases like the agnosticity of saliency maps. One example of saliency methods have actually been used in a paper that came out of the Rajpurkar Lab, Checks Localize. And here the researchers established a human benchmark for chest pathology segmentations. And upon applying different saliency methods, including GradCam, they were able to run different input images through some CNNs and generate heat maps for chest X-ray pathologies and convert those heat maps to binary segmentations. And what they were able to discover is that when you look at the model's ability to generate a segmentation, it's not pretty good compared to the ground truth segmentation. It's looking at a really broad area. But if you look at the sort of central area, like you can see this pink point here of the saliency method segmentation, it actually falls within the region of the ground truth segmentation. So that gives some confidence that the CNN models are actually looking at the correct regions of an image when they're making a prediction about a pathology. So that was a lot of information right there, but just one important thing to take away from saliency methods is that they are basically attribution heat maps, and they allow you to understand how important an individual feature or pixel is to the final class prediction. So our next approach is LIME, Local Interpretable Model Agnostic Explanations. And as the name suggests, this approach is agnostic. It has a local scope. It is actually one of the most popular approaches or XAI techniques for a lot of researchers because it has an application to any sort of data modality, and it's black box. So you don't really need to know the internals of the model to do anything with LIME. And the idea behind LIME is that if you have a global decision boundary that's really hard to explain, maybe you don't need to understand every single aspect of that global decision boundary. So for example, let's say I have this AI model that's classifying whether a patient is at risk for stroke or not. And this pink patient is the one that I care about. I don't really need to know why the decision boundary has a peak on this left side. I kind of care more about this local region here at the decision boundary, which is causing this patient to be classified as a high risk for stroke. And visually observing this, simple case where we have two features, we can see that the basis for the decision might be feature 2. It looks like feature 1, that Y direction, doesn't seem to be having a big impact on the decision, but where you are on feature 2 does seem to influence, whether you're going to be predicted with stroke or not. And the way we were able to do that is we were able to kind of zoom in on the global decision boundary and say, I think this dashed line kind of represents a local decision boundary. And that's what LIME is actually going to do for us. It's going to help us make a local linear model, and this is often called a surrogate, to a region to help us understand what features are causing a decision to be made in that local region and really understand that local behavior. So then the question comes, how do you find a surrogate model for that local area? And the optimate surrogate model is going to minimize this kind of complicated looking equation. It's actually not too bad. We're going to break it down into a few pieces, and then it'll make a lot of sense how LIME actually finds a surrogate model. So the idea here is to work with a family of interpretable functions. So this could be linear regression, logistic regression, and these are going to be potential surrogates that we want to use. And we're going to go ahead and try to compute the loss or the difference between the predictions generated by the surrogate model and the predictions generated by the global decision boundary. So over here, we're treating the global decision boundary as sort of our ground truth, and we're treating the surrogate model as the model that we're trying to train. And I'll touch on proximity in a second. We also have this regularizer here to make sure that we're choosing the simplest possible surrogate model. So how do we actually train the surrogate model so that we can find this loss and optimize this equation? There's two main steps. The first step is to generate a lot of fake training data near that local region. The reason we need to do this is because if you look back, for example, at this big map here of all of our training data, it's really spread out, and we don't have a lot of training data in our actual local region. So we need to make some perturbations to the pink input to generate fake training data that we can use for our surrogate model. So this could look like tweaking a few pixels, masking some words in text, or like changing different columns in tabular data. And you can see that some of the generated examples are more similar to the input and some are not as similar. And the idea here is that when we actually train on the surrogate model with this training data, we should be able to make a prediction for these simulated examples and compare it to how close it is with the input that we actually care about. And we just do this with a simple least mean squares. That's where this proximity comes in earlier that I said I was going to talk about. You can see that some of the examples are closer to the input and some not so much. The examples that are closer to the input are more similar to what we're trying to understand. So we want to give them more weight in the loss, and examples that are farther away are not as important. So we probably don't want to give them as much weight in the loss. So that helps us come up with a way to quantify how close our linearly interpretable surrogate model is to the global decision boundary, and we just take the differences between the predictions. Now, going back to this regularizer portion over here, why do we even need to regularize for a simpler surrogate model? The idea behind it, or the intuition behind it, is that let's say you're trying to understand, let's go back to like this stroke. Let's say you're trying to understand what features are causing the linear decision boundary to look this way. Assume, just for the sake of example, that instead of 2 features, we have 10. It's really hard to interpret 10 features, but if we have some sort of regularization, that'll push a lot of the coefficients to go towards 0, and the coefficients that are left over will essentially reduce the number of features that are actually relevant in our equation. And the less features there are, the easier it is to understand the intuition behind the surrogate model. So that's why we're trying to apply a regularization technique in this optimization equation. So overall, like LIME is pretty useful in real world context. Like a really good use case is seeing whether your model's global decision boundary in that local region verifies prior knowledge. So in the stroke example, that could look like, let's say a patient who is on the left side of this decision boundary and is classified for stroke. Turns out that that's the case when you exercise a lot. And that doesn't seem to make sense. Like if you exercise a lot, you probably should be at lower risk for stroke. But now that we have an understanding of the feature that high exercise means high stroke, we know that we've done something wrong with our model, and we can kind of zoom in and debug better. Local information is not always the most helpful either. Like if you're working with, let's say like a sepia toned image and you want to understand whether it's retro or not, zooming in on a local region of that image probably won't tell you much. So there are definitely particular use cases for Lime, but when you do need local information, it is pretty helpful. That was like very theoretical. A good example of this would be this paper, Gabe et al., which came out in 2020. They used Lyme to understand what made a 70-year-old patient predicted at high risk of severity for COVID. So they basically trained an MLP model that took in a lot of different personal information, as you can see on the column on the right, and they outputted the severity of risk for COVID. And by applying Lyme to this MLP, they were able to figure out that some of these features shown on the right were particularly influencing the prediction to go towards high severity, and others were suggesting that the patient was at low severity. And ultimately, the explanation indicated that at the time of prediction, the patient's main symptoms and medical history that most contributed to this high-risk prediction was pneumonia, his age, his diabetes, and his chronic renal failure. So it really helped isolate the features that were actually relevant to the prediction. And we didn't actually end up caring about pregnancy, for example, because that was not relevant to this patient. So like maybe one way to think about this is kind of like PCA. It helps you really isolate the most relevant features for a particular prediction. So now we've looked at two techniques, Saliency, which helped us understand attribution heat maps, and Lyme, which helps us understand how certain features explain decisions in a local region. We're now going to jump into SHAP. SHAP stands for Shapley Additive Explanations. It is also a feature interpretation approach, and it's based off of a game theory concept known as the Shapley score. The scope of SHAP is very similar to Lyme, and Lyme and SHAP do actually have a lot of overlap, but you'll see some of the nuances as we move forward. The idea behind SHAP is that we're essentially trying to understand what is the contribution that each feature has to a prediction relative to all predictions. So in Lyme, we were looking at the contribution of a feature to a prediction in a local region. And in SHAP, we're looking at the contribution of a feature compared to other features there. So this can be like a little difficult to wrap your head around. So I'm going to walk you through kind of a real world analogy for this. So let's say these circles here are 5 different people working on a group project for an ML class, and they're trying to predict stroke. This person here is a deep learning expert, and this person on the right is a systems expert. And let's say as a whole, this group is really solid. They get an A+ on their project. Let's say now we remove the systems expert from the team. Now the team is getting an A, which is still pretty good. And it kind of makes sense because systems is not super relevant to the stroke prediction task at hand. So if we didn't have the systems team member, it wouldn't make that much of a difference. But let's say we look at a different scenario where we take the deep learning expert off of the team. Now all of a sudden the team is getting a C on this project. And that shows that the deep learning member has a huge contribution to the team. On the flip side, let's say out of these 4 members, we remove the systems expert, maybe we'll get a lower C. We won't actually have that much of a difference because our main contributor, the deep learning expert, was already gone. And to have the systems expert removed furthermore doesn't make that much of a difference. So if we were to do this with all possible sub-teams, then we would get an understanding of how much each group member contributes to the project. And that's kind of the idea behind SHAP. Basically says, let's take all the possible subsets, let's remove one group member and figure out what changed in our prediction. And let's quantify it and average over all the subsets so we know exactly how much each person's marginal contribution is. And within the scope of AI, this isn't group members for a project, this is often features for a model. So then the question comes, how do we actually quantify this? How do we calculate the Shapley score? Again, we have sort of a fancy looking equation, but it's actually not too scary. The idea behind Shapley score calculation is let's take our input model and let's take all of our features X. Sometimes we're going to be working with X prime, which is basically like less features than X. Maybe we don't need all the features. Like an example of this could be pixels in an image. Maybe you don't want to use all the pixels, so you're going to over segment and use a downsampled version of the pixels. But the idea is you're going to have almost all the features available, and Z prime is like a subset of the features. And for each of these subsets, we are going to try to figure out the change in class prediction probability after you remove feature I and weight it using some factor. So the weight itself, if you notice, is kind of complex and it's based on a lot of different things. M here is actually the size of X prime. It's the number of features we're working with. Z prime is the size of the subset, and M minus Z prime minus 1 is the amount of features that are left over after we take out that subset, as well as the feature of interest I. And the sort of big question over here, as we're computing Shapley, is how do we actually remove a feature without changing the structure of the model? If you look at this equation, we're trying to make a prediction using only Z prime as features, and we want to remove I. But if we remove I, then that would change the architecture of the model, and that would change the weights. So sort of a workaround here is that we don't actually remove the feature from the model. We just simulate its removal by adding a bunch of random like numbers or pixels or text words in the place of that image or text. And the idea behind it is that a feature that is randomly distributed doesn't actually contribute to the output. So we can simulate removing it by essentially randomizing it inside of our distribution. So by doing so, we can then understand what the prediction probability would look like. So maybe if we kept the deep learning expert on our team, the probability of getting an A+ would be 100%. And if we take out the deep learning expert in our team by randomizing their contribution, then maybe the probability of getting an A+ is now 10%. And we have a quantifiable difference that we can use. Jumping back to the weights, we were looking at the size of the subset and the opposite of the subset. Why do we care about both? Well, let's say the size of your subset is really big. Let's say you're looking at all of the features in your model and you're trying to figure out how important this change is. Let's say this change, like in the case of our deep learning expert, is going from 100 to 10%. That's like a 90% change. It's making that big of an impact, even with such a big set of features. That means it must be really important. On the flip side, if Z prime is really small, let's say there's only 2 features we're looking at, and we find a really big difference, that's also important because that means we're isolating feature I and understanding its individual contribution to the model. So we basically have a way of weighting both extremes, and we're now able to understand overall how each feature is contributing in the subsets. So as you can tell, there's a lot of computation involved in SHAP. Not only do we have 2 to the n different subset combinations, but we also have to find model predictions and compute these losses and do these weightings and summations. So it can get really computationally expensive given how simple of a task we're trying to do. So that's where some different approximation methods come in. One of the most popular ones is kernel SHAP. So it basically does a kernel approximation black box model, and it treats the coefficients of the features as the Shapley scores instead of computing the Shapley scores themselves. This can still take a lot of time, and in practice, kernel SHAP isn't used that much yet. The model that is used most frequently is tree SHAP. Tree-based models are currently the easiest ones to compute the Shapley score on. So there's definitely a lot of great applications for SHAP in theory, but there's a long way to go here. And if somebody can figure out an easier and faster way to compute a Shapley score for a model, then it would have a lot of utility in understanding feature contribution. So let's take one more step back. We talked about saliency, which were the attribution heat maps, LIME, which told us how features explain decisions in a local region, and SHAP, which helps us understand how important a feature is relative to other features. So saliency, LIME, and SHAP were all really important for feature explanation. We're now going to actually pivot a little bit and try to understand how inputs or training data influence our model. So that's not exactly the same as features because features are attributes of the training data. And when I say inputs or training data, I mean the data set as a whole. So understanding the distribution of the data or particular examples of the data, because that too influences how our model performs. And XAI can be really helpful for understanding whether our training data is suitable for our model needs or not. So today, we're just going to look at one type of input attribution XAI, and that's called counterfactuals. There's sort of two broad camps. There's the adversarial type, and there's the prototype-based explanations. So the idea behind counterfactuals is that we want to understand what is the smallest change you can make in an input so that you can completely change the prediction to a different target output. So, and in this math equation, we can see like X is the input, X prime is the change input, and we're trying to make f of X prime some class C. This is like applicable to both a global and local scope, and you don't really need to understand the model. So it's black box and agnostic, and you can also do this with tabular data or image or text. The way adversarial attacks approach this is by saying, hey, how much do I need to change my input so that I can trick the model? And it actually makes changes in the input data and feeds it into the model. So an example of this is this 2022 paper, Matsui et al. They came up with a counterfactual activation generator, and this activation generator ran adversarial attacks against a deep neural network classifier. So this classifier takes in different fMRIs of brain activations, and it outputs the task that the brain is doing. So for example, the one on the left is classified as doing a motor task. So we see that the model has correctly classified it, and the adversarial attack, the generator essentially tries to skew a few of the pixels until the DNN classifier predicts it as a motion. So you might wonder, why are we changing the pixels? Like, why do we care what it takes to go from motor to emotion? And the end result here is that if you do this with a bunch of training examples, then you get a sort of average map of what pixels had to be changed in order for the model to make a difference between motor and emotion. And it adds a layer of granularity to what emotion really means in an image. And on the flip side, where emotion over here is being misclassified as social, if you change a few pixels until the deep neural network classifier predicts it as emotion, it helps you better understand what were the specific localized reasons that the image was being misclassified. So overall, adversarial attacks are giving researchers an opportunity to learn about very specific granular changes that causes the model to behave one way, how specific parts of the input are influencing the output itself. And in the context of this paper, the researchers were actually able to learn about a novel texture pattern inside of brain activation maps that are symptomatic of different tasks. And this is something that radiologists actually didn't know earlier. To date, radiologists were looking at the activation map as a whole and sort of interpreting broadly what task it reflected. But through these adversarial attacks, we now have a better sense of what the texture of this map should look like in order to reflect a certain emotion. So the second type of counterfactual XAI technique is prototype-based explanations. And it's kind of as the name sounds, we're trying to get an understanding of what our prototypical input looks like and what an outlier input looks like. And this technique is really helpful for understanding which training examples made the biggest impact in our model's learning process. Which training examples most influence the parameters that were learned by the model. I also like to think of this one as PCA for a training data set because you're evaluating the relative importance of training examples, but it's PCA for like training examples and not exactly features. So prototype-based explanations rely on the idea of removing a training example and recomputing the parameters to see how the predictions would change. Essentially, this tells us how dependent the model is on a training example, because if the parameters change drastically, we know that that training example was super important. So normally the sort of vanilla way to do this is called deletion diagnostics. This is essentially where you delete the example, retrain the entire model, and see how the predictions changed. As you can tell, that would probably be really, really expensive. So instead we use something called an influence function. And these two equations here represent how that influence function is structured. So in SHAP, we observed removing a feature by randomizing the feature. In prototype-based explanations and influence functions, we observe the removal of a training input by actually upweighting its value in the loss function. So if you look at this top equation here, the left part is the loss of all of the training inputs. And we add a very, very small upweight to the particular training input that we care about. The math behind this is a little bit complex, but essentially by upweighting the loss, the other training inputs now have to compensate. And if they have to really compensate a lot, that means that the training input was super valuable to the training process. And if they don't have to compensate too much, that means we know that the training input that we upweighted too important and the model parameters wouldn't change too much. When it comes to actually computing this change in loss, that also can be really computationally expensive. So we use a quadratic approximation, and that's where this influence function comes in. So this is getting a little bit mathy, but just to sort of break it down at a high level, we approximate the change in loss by upweighting an example by taking the Hessian of the gradient of the loss with respect to the parameter. And I can definitely answer some questions later if anybody has any questions about how this works. But I think just the most important thing to take away is that the influence function allows for us to approximate the change in loss when you when you upweight a training example. One thing to keep in mind though is that this loss function does have to be a second order differentiable function in order for the influence function to work. And what we end up with is influence scores for each training example. And the larger the magnitude of that influence score, the more significant the training example. And the smaller the score, the less significant the training example. And overall, influence functions are really helpful in identifying test and train domain shifts, for example. So if a good example of this might be, let's say you're trying to classify lung pathology within a chest x-ray, and you've trained your model off of images that came out of one hospital. And the training score looks great, validation looks great, test looks great. But as soon as you deploy this trained model inside of a different hospital, now it's doing poorly. So in order to debug, the sort of efficient way to go about this is to figure out what were the things in the training inputs that were different in one hospital between another. And by using functions, maybe you'll figure out that some of the outlier examples in the training inputs were ones where the age was drastically different from the average age. And through this insight, maybe you'll realize that your hospital, which you use for training, actually had younger patients, and the hospital where you deployed had older patients, and that actually influenced the training results. So now you have an understanding of training and test domain shifts, and you can debug accordingly. Overall, these influence functions give you a mental model of a good training input in the same way that we as humans, like if I say, what is a dog? You have like an idea of what aspects are needed for a dog. And you can also think of some outlier examples for like an extreme looking dog. In a medical use case, this has actually been really, really helpful. There was a paper, Ko and Liang in 2017 that was trying to figure out when can you release a patient from a hospital who was in a critical condition when they entered the hospital. So they found that instead of looking at model loss or model validation to figure out what sort of patient is the most representative of a critical patient, you can use influence functions to figure out outlier patients that are in very critical condition. And you can then take your current patient and compare them to this outlier. Do they look more like the outlier critical patient, or do they look like the prototype and can be released? So prototype-based explanations give us a really good sense of what a good training input looks like and what outlier inputs are influencing our model. The only downside to this is that influence functions don't have like a concrete benchmark per se, where we can say, oh, like if you have this score, then you're influential. And if you have this score, you're not influential. It's all relative. So if you try to find out the top 10 influential training inputs, maybe only the top 3 matter, but you won't actually be able to figure that out. So it's definitely a shortcoming within the counterfactual space, but where prototypes have been used, we've seen some pretty great rewards. So, okay, that was a lot on counterfactuals, but it's clear now how they differ from feature attribution approaches. With saliency, we were looking at the attribution heat maps, LIME, how the features explain decisions in a local region, and SHAP, how features work relative to other features. And with the counterfactuals, we saw that we were making changes to the input to change the prediction. And in particular with prototype, we were getting a better sense of what a typical training input looks like and what an outlier training input looks like. So, now you've learned about a couple of different techniques. How do you decide which XAI approach is good for you in understanding whether your model is performing a good way or not? I found this guide to be really, really helpful. It's called Interpretable Machine Learning by Christoph Molnar. It covers XAI theory for various different approaches, goes deep in the math, and it also has some coding use cases. And there's also a lot of new papers coming out, especially with variations on LIME and SHAP. So I highly recommend looking into those approaches, especially because they're black box and model agnostic and very broadly applicable. But if you have a very specific use case, then this book also goes into details of white box approaches and the research spaces that are developing them. So now we're kind of near the end of our presentation, and we've talked about a lot of things, and there was a lot of technical details that came in the way. But I think the sort of main things to take away is the reason we need XAI is to create trust, accountability, and better understanding of models so that we know that they're making decisions correctly. There was a sort of famous use case outside of the automatic grading systems that talked about a model that was trying to predict between a wolf and a husky. And the model itself was doing really well, but researchers found out that it didn't actually look at the animal when making a prediction. It just learned that husky pictures usually have a snow background, so it was looking at the snow. And the model actually wouldn't do too well when deployed in real life. So keeping this example in mind, definitely place a high value to XAI when you're working on medical AI models, because these kinds of things can happen. We talked about some leading XAI techniques like saliency maps, LIME, SHAP, and two branches of counterfactuals, adversarial and prototype. These approaches are very broad and applicable, but we can definitely also find more model-specific approaches. And lastly, in order to find an XAI approach that fits your specific need, you should query based on scope, purpose, agnosticity, and data modality. And hopefully you'll find a technique that can allow you to better interpret what your model is doing and why it's doing it. So yeah, that is sort of an overview of XAI and why it's important. And I hope you have a better understanding of it now.
Thanks, Priya, for the wonderful talk.